Hello and welcome back. This is our fifth lecture, chapters 10.5 and 10.6, probability using permutations and combinations and odds. Let's begin. We're going to start off with an example. Stacy has the option of selecting 3 books to read for a humanities course. The suggested book list consists of 10 biographies and 5 current events books. She decides to pick 3 books at randoms. Find the probability that all 3 books will be biographies. We first need to identify whether or not this is permutations or combinations problem. Well, it doesn't say we care the order in which the books are chosen, so we do assume it's combinations. I'll go ahead and recall that formula for y'all. First, we'll figure out how many ways in which we can choose a biography. So from the list of 10 biographies, we want to choose 3. So that means we have 10 to pick from, and we're choosing 3. So we get 10 factorial divided by 10 minus 3 factorial times 3 factorial, which is 10 factorial over 7 factorial times 3 factorial, which is equal to 10 times 9 times 8, divided by 3 times 2 times 1. This is equal to 120. So there are 120 ways in which she can pick 3 biographies. Next, we'll figure out how many total options there are to choose a book in general. So in general, there are 10 biographies and 5 current events, which makes 15 to choose from. Of these 15, we want to choose 3. So that's going to be 15 factorial divided by 15 minus 3 factorial times 3 factorial, which is 15 factorial divided by 12 factorial times 3 factorial, which is equal to 15 times 14 times 13 divided by 3 times 2 times 1, which is 455. So we have 455 total choices, and we have 120 ways to pick 3 biographies. That means this 120 represents my number of events, and this 455 represents my number of outcomes. And since probability is just the number of events divided by the number of outcomes, that means that the probability of 3 biographies is going to be equal to 120 divided by 455, which is approximately 0.264. Moving on. What is the probability of getting 4 aces when drawing 5 cards from a standard deck of 52 cards? The first thing we'll need to do in order to solve this problem is figure out how many 5-card hands exist. We know that we can't repeat cards because the same card cannot be dealt twice. There's only 1 of each card. But we also don't care the order in which we are dealt cards. That makes this a combinations example. So we'll have 52 cards, and we are choosing 5 of them. That means we have 52 factorial divided by 52 minus 5 factorial times 5 factorial. This is equal to 52 factorial divided by 47 factorial times 5 factorial, which is equal to 52 times 51 times 50 times 49 times 48, divided by 5 times 4 times 3 times 2 times 1. It equals 2,598,960. And remember, all we found so far is the total number of possible hands that can be dealt. So this is our number of outcomes. Now we need to figure out how many events that we have. So we want 4 aces. So if I have a hand of cards, right? I'm going to draw you a little picture. I have 5 cards, 1, 2, 3, 4, 5. I want all of these to be aces, and it doesn't matter which ones, so you can just kind of randomly assign the suit. We don't care the order of the aces. But this last card, now how many choices do I have for this last card? Well, I already have 4 cards I've pulled out of my deck. So 52 minus 4 is 48. So this spot has 48 choices. As a matter of fact, this means we have 48 hands to choose from, because whatever card I put in this spot, whatever choice I make is going to be the hand that I desire. So for example, if I pick the 3 of diamonds, this is a hand that I want. And it really doesn't matter which card you pick. You could also have picked the 10 of spades. And this is still a hand that I want. So that means we have 48 total choices for our events. Thus, the probability of getting 4 aces is equal to 48 over 2,598,960, which is approximately 0.00000185. Very low possibility. All right, moving on. A combination lock has 40 numbers on it, from 0 to 39. Find the probability that if the combination to unlock it consists of 3 numbers, it will contain the numbers 1, 2, and 3 in some order, and we assume that the numbers cannot be repeated. So it is called a combination lock. However, since we care about the order, because your lock having the combination of 1, 2, 3 is different than it having the combination of 3, 2, 1. And it's the same with passwords, right? Like your phone password. It depends on the order the numbers are in. So this is a permutations problem, if you couldn't guess by the title of this slide. So first we need to figure out how many ways that these 3 numbers can be ordered. Now remember, we can use the permutations formula for this, which would be 3 choosing 3, which is just 3 factorial. 3 times 2 times 1, which is 6. You could also have thought about this a little bit more conceptually, where you have 3 spots for 3 numbers. And in the first spot, you're choosing 3 numbers. And then in the second spot, since you've already chosen a number, you only have 2 left over. And the last part would have been 1, which is still 6. Either way that you like to think about how to solve these problems is perfectly valid. Next, we need to figure out what is the total number of outcomes. So we know we have 40 numbers on it, right? And we're only choosing 3 of them for a combination. So that's going to be 40 factorial divided by 40 minus 3 factorial. Oh, well, we call y'all the formula as well. That's n factorial over n minus r factorial. So this is equal to 40 factorial divided by 37 factorial. It is equal to 59,280. So this is my number of outcomes. And this 6 was my number of events. So the probability of a combination containing 1, 2, and 3 is equal to 6 divided by 59,280, which is approximately equal to 0.000101. Moving on. Next, we'll talk about how to find odds. Odds provide a comparison between the number of favorable outcomes and the number of unfavorable outcomes. If an event E has A favorable outcomes, so A represents a number here, and B unfavorable outcomes, then the odds in favor of event E is A divided by B, or you can write it as a ratio A to B. And the odds against E occurring is B over A, which can also be written as the ratio B to A. So let's compute the odds. I know that there are 4 aces. We also know that there are 52 cards, right? So that means the number of cards that are not an ace are 52 minus 4, which is 48 cards that are not an ace. So getting an ace is my favorable option, right? Because in favor of getting an ace. So that means I'm going to have my favorable divided by unfavorable according to this formula, right? A favorable, B unfavorable, A over B. So that means I have 4 over 48, which is equal to 1 out of 12. And you can also write it as 1 to 12. Find the odds against getting an ace. Well, if the odds in favor of getting an ace are 1 over 12, the odds against it would be the reciprocal, which is 12 over 1, or 12 to 1. You can see this again in the formulas because the odds in favor are A over B, and the odds against are B over A, which means when you're going between odds in favor and odds against, you're just using reciprocals. So you're just flipping that fraction. Okay? So moving on, you can also use probability to determine the formulas for odds in favor and odds against. So the probability of getting exactly 1 pair in a 5-card poker hand is 0.423. Find the odds in favor and the odds against of getting exactly 1 pair. So first, we know that the probability of our event E is equal to 0.423 because it's given here. Our event E is getting exactly 1 pair. So this is E. And we're given the probability of that as well. So that means the odds in favor are going to be 0.423 divided by 1 minus 0.423 using this formula right up here. This is equal to 0.423 divided by 0.577. We want these to be whole numbers though, so let's multiply by 100 over 100 to get it to be 423 over 577, or as a ratio, 423 to 577. Next, we are going to do the odds against, and we're going to use this formula. So we'll have 1 minus 0.423 divided by 0.423 which is 0.577 over 0.423. Can multiply that by 100 over 100. So that's 577 over 423, or 577 to 423. Okay, moving on. Next, you're going to learn about expected value. Expected value is used to determine the result that would be expected over a long term in some sort of gamble. So the expected value formula is this, where the x's correspond to the numerical outcomes and the p of x's are the corresponding probabilities. However, you can also think about expected value as the value of event 1 multiplied by the probability of event 1, and then you add as you increase your amount of events. So value of event 2 times probability of event 2, and et cetera, depending on how many events you have. So the x's correspond to the value of that event, the numerical outcome, and the p of x's are still the probabilities. Let's do an example where we need to compute the expected value. 1,000 tickets are sold at $1 each for 4 prizes of $100, $50, $25, and $10. What is the expected value if you buy 2 tickets? So it is important to note that there are only 4 winning tickets, right? Because it says 4 prizes. So the probability of getting a winning ticket is going to be 1 out of 1,000 for each of these values. So if we win a $100 ticket, we actually only win 99 because we spent $1 on the ticket. And that's going to go the same for all the different values. So our gains are going to be $99, $49, $24, or $9. Also, losing $1 if we don't win at all. So there is a possibility we can have a loss. The probability of each event is, well, to win $99, that probability is 1 out of 1,000. And the same for all of the other values, because there are only 1 of these tickets, and there are 1,000 total. However, since there are 4 winning tickets, that means there are 996 losing tickets. Now we can plug this into our expected value formula. So we'll have 99 multiplied by 1 over 1,000 plus 49 multiplied by 1 over 1,000 plus 24 multiplied by 1 over 1,000 plus 9 multiplied by 1 over 1,000 minus 1 multiplied by 996 over 1,000. Since our expected value formula tells us we need to do the value multiplied by the probability of the event. And then we add them all up. So the expected value is going to equal negative 0.815. However, we need to multiply by 2 since we bought 2 tickets. So that means our expected value is equal to negative 1.63. To explain what expected value is a little bit more conceptually, we're thinking if we do this event multiple times. So this lottery game, if you will, these 1,000 tickets being sold, we go every single day for a year and we buy 2 tickets. And we may have won and we may have lost some. But overall, in general, you can expect to lose about $1.63 every time you buy 2 tickets. That's what this means. So even though you may have won $100 1 or 2 times over all of the times you played this game, on average, you lose $1.63 every time you play this game. That's what expected value means. All right, thank you all again for tuning in to our online lectures. This concludes our 5th lecture. And again, I hope you have a wonderful rest of the day.